In this video, we'll explore one of the simplest and most intuitive algorithms in machine learning, K-nearest neighbors or KNN. By the end, you'll understand how it works for both classification and regression, why it's powerful as a first step in AI, and where it struggles in the real world. Welcome to AI Club Pro, where we make AI concepts feel like everyday ideas. Before we dive in, let's quickly set the stage. Machine learning works with features and labels. Features are the inputs, the information that we already know. Labels are the outputs, the answers we want to predict. If labels are categories like pass or fail, cat or dog, we call it classification. If labels are numbers like house price or temperature, it's regression. KNN is flexible. It can do both. So how does KNN work? Imagine you move to a new city and want to guess if a restaurant will suit your taste. The fastest way? Ask your neighbors, people with similar preferences. Exactly what KNN does. It looks at the closest data points and decides based on them. So let's start with a classification example. Suppose we have a dataset of fruits with two features, weight in grams and sweetness level on a scale of 1 to 10. You can see a sample dataset over here on the screen. Apples are lighter and sweeter and oranges are heavier but less sweet. If we plot this in two dimensions, red points are represented by oranges and green points by apples. Now suppose we have a new fruit that has a weight of 190 grams and a sweetness of 6. KNN looks at the k nearest neighbors. If k equal to 3, the two of the nearest are apples, then the fruit is predicted as apple. But how do we measure nearest? The most common is the Euclidean distance, the straight line between 2 points. Others include Manhattan or Minkowski distance. The choice of distance metric can change the results, especially in higher dimensions. Now let's see regression. Suppose we want to predict house price using two features, age of the house and square footage. Here's a sample dataset to demonstrate this. For a new house that is 8 years old and 1,550 square feet, KNN finds its nearest neighbors and averages their prices. That average becomes the prediction. An interesting property of KNN is that it's a lazy learner. It doesn't build a model ahead of time. Instead, it stores all the training data and makes predictions when needed. Is that just memorization? Not quite. Behind the scenes, efficient data structures like KD trees or ball trees speed up, especially when datasets are large. KNN isn't perfect, and here are a few limitations that it faces. The first one is feature scale sensitivity. KNN relies on distances to decide who the nearest neighbors are. But what if your features are measured on very different scales? Let's revisit our house price prediction example. Imagine we are using two features, age of the house in years and size of the house in square feet. Suppose we want to predict the price of a house that is 0 years old and 2000 square feet. Now look at two possible neighbors in the training set. House A, that is 30 years old and 2000 square feet, and house B, which is 0 years old and 1900 square feet. Intuitively, house B should be closer. Same age, slightly smaller size. But here's what KNN sees if we don't adjust the scales. Distance to house A is 30, all from the age difference, and distance to house B is 100, all from the size difference. KNN says house A is closer. But that doesn't match reality. Buyers care much more about age than about a small difference in square footage. This happens because the numbers themselves are on different scales. Age ranges from 0 to 50 and size ranges from 1000 to 5000. So the size feature dominates the distance calculation. even though it may not be the most important factor. So how do we fix this? One can do this by scaling the features so they contribute equally. Two common methods are normalization, where you rescale all features to a 0 to 1 range. For example, if a house age is between 0 and 50, then 30 years becomes 30 over 50, which is equal to 0.6. If the house size is between 1000 and 5000, then 2000 square foot becomes 0.25. Now both features are on the same 0 to 1 scale. Another method you can use is standardization, where you shift features to have a mean of 0 and a standard deviation of 1. This is useful when ranges are unknown or features have very different distributions. Once we rescale, distances become meaningful again, and KNN makes the right choice. A second issue that KNN has is the extrapolation problem. KNN is great at copying patterns it has already seen, but it cannot extrapolate. It can't predict beyond the range of its training data. Let's return to our house price dataset, where we are predicting the price using age of the house and size in square feet. The data we have covers homes up to about 2,000 square feet in size and prices between $180,000 to $500,000. Now suppose we want to predict the price of a huge house that is 10,000 square feet, brand new, so 0 years old. Here's the issue. KNN doesn't extrapolate. It simply looks for the nearest houses it has seen. In this case, the closest neighbors are still small compared to a 10,000 square feet, like 2,000, 1,800, 1,700 square feet, etc. KNN then averages their prices around $500,000, $420,000, and $260,000. That gives a prediction of about $393,000. But think about it. A 10,000 square feet mansion priced the same as a modest 1,800 square feet house. That's clearly unrealistic. This happens because KNN is interpolative. It fills in the blanks between known data points. But when you ask it to predict beyond the largest size it has ever seen, it simply copies the closest examples. It cannot extend the trend. That's what we mean when we say KNN cannot extrapolate. If you need predictions outside the training range, KNN is the wrong algorithm to use. For this, you'd use models that can capture trends, like linear regression or gradient boosting, or even better, collect more training data that includes the type of homes you care about. So remember, KNN is excellent at interpolating within your data, but don't expect it to imagine what lies beyond. The third limitation that KNN has is the computation. With huge datasets, searching neighbors becomes slow. When the datasets are huge, indexing and approximation methods help. Another limitation is the curse of dimensionality. As features increase, distances lose meaning. Dimensionality reduction techniques like PCA can help. KNN is simple, visual, and intuitive. It teaches the core idea of machine learning, which is decisions by analogy. That's why KNN remains a classic in machine learning. So that's a wrap. Thanks for joining us on AI Club Pro. Hit that subscribe button for more eye-opening AI stories and insights. Stay curious and keep exploring.